Hello, welcome to my channel. So in today's problem, we have here a how many rods? We have three rods here: the pink, the green, and the blue. Now let's consider these rods to be massless, and let's consider the friction on these pivot points where the one rod rotates relative to the other is frictionless, and this one is fixed, and this one rotates relative to the pink, and the blue relative rotates relative to this green here. This so we are asked to find the equations of motion of the system. Okay, here it rotates at a rate of alpha dot. Here it rotates at a rate of beta dot about this axis, and this one rotates at about theta dot, beta dot, theta dot. Okay. First, let's give lengths to this rods. Okay. Let this be of length p, and while this one is of length q, and this is r. Both of this, it is assumed to be at the pivot is at the center of the rod. Okay, so next is we form the vector from the origin. Let's take the fixed point to be the origin. This will be our origin. I write it in yellow. That will be our coordinate system. And to get from this point to the mass, we will have three vectors. First vector is that, and then this, and then that. Okay, so let's have this three vectors. Pink, the pink vector is this, and then we have the green. Where's the green vector? Is that, and then the blue vector. Okay, let's call the pink the p vector. Okay, this is the p vector, the q vector, and this one is the r vector. So to get to the first mass, the position vector of first mass of the first mass m is, let's call that x1. That would be equal to p plus q plus r. While this one here, for the second mass, x2 would just be equal to p plus q, and this is minus r because it's on the opposite direction of this of the blue vector. So we now have our um, position vectors. We can calculate now the kinetic energy. Okay, what is the kinetic energy of the system? The kinetic energy is just equal to the sum of the kinetic energies of the two masses. So you have now 1/2 m x dot squared, x1 dot squared plus 1/2 m x2 dot squared. Okay, so we're done actually if we know x1 and x2, but but for this we need first to calculate x1 and x2. Okay, now let's calculate p. What is the vector p? Let's think of the generalized coordinates first. Let this our generalized coordinates alpha. This one is beta, while this one is theta. Okay, so the p vector now will be given by the vector p. Where did I write it? Okay, the vector p will be given by p cosine of alpha I hat plus, or we can take this as a minus because it's downwards. So p sine of alpha j hat, and of course x dot here, x dot 1 is just equal to p dot plus q dot plus r dot. So all we have to do is calculate these vectors. Now this is actually the length of the p is constant, it doesn't change, and p, q, and r, these lengths doesn't change. so that our p dot only changes in terms of alpha. But for the sake of this lecture, I'll be calculating the general form of p dot. Okay, so let me calculate the general form of p dot, assuming that both p and alpha are changing. So we have now p dot, that would be this one here. Okay, that would be p dot cosine alpha plus first the second plus second the first. Now you will have now here a minus. You have alpha p sine of alpha, because the derivative of cosine is negative sine. Sine of alpha I hat um, minus. So again, we will have here p dot plus p dot sine of alpha plus alpha. Sorry, this is alpha dot here. Alpha dot cosine of alpha j hat. Okay, so that would be our p dot. So that means that our p dot squared would be equal to, we have to square this, we have to square the both components. So the square of this one is just equal to p dot squared cosine squared alpha, and this is minus 2 alpha dot alpha dot p dot p sine alpha plus alpha dot squared p squared sine squared of alpha, and we have here plus, right in the second line, um, we would have now the square of this is p dot squared sine squared alpha plus 2 alpha dot p sine alpha. Okay, sorry, there is a cosine alpha here. Okay, sine alpha cosine of alpha plus, you would have alpha dot squared p squared cosine squared alpha. Okay, so here clearly this would cancel out, and what is left is that we have p dot squared plus p dot squared cosine squared plus p dot squared cosine squared sine squared. This is just p squared, because when you factor out p, you will have cosine squared plus sine squared. So you have now p dot squared plus, in this case you have the same thing. So that you have alpha p squared alpha dot squared. So this will simplify now to p squared alpha dot squared, okay, times 1, because sine squared plus cosine squared is 1. Okay, so this will be our p dot squared. Now in the case of our problem, p is actually constant. So in our problem, specifically in our problem, our p now would be equal to just p squared alpha dot squared. That would be our p dot squared. What's our p vector? Our p vector is just equal to um, p alpha dot alpha hat, because it's going in the alpha hat direction. This is alpha hat direction here, meaning we only have an angular displacement, no translational. That's why this is alpha dot. Okay, so this is true for all, for q dot and for even r dot. Okay, so now let's calculate now x dot. Our x dot, okay, our x dot is the square of this one, so let's take that square. X dot squared would be equal to, let's square this, so I'll just group these two. So I would have p dot squared, okay, okay, sorry, that is p dot plus q dot squared plus 2 times p dot plus q dot dot r dot plus r dot squared. Okay, this is x1. And what about x2? Notice that our x2 dot squared would be equal to p dot plus q dot squared. And since this is negative for our q dot, then this would be equal to minus 2 p dot plus q dot dot r dot plus r dot squared. And notice that this will cancel out. Okay, so since we have actually the same masses, so the sum of the kinetic energies here is just the same. So we can just combine this. So in fact, our total kinetic energy now, that would be equal to T is equal to um, M plus M. You have 1 half M plus 1 half M. That's M. Okay, this should be M times X dot 1 squared plus X dot 2 squared, which is just equal to um, 2M. No, there's no 2 there. You have M times P dot plus Q dot squared plus you would have R dot squared. So this will be our kinetic energy, and we can just factor this one out. I mean, we can just expand this one, in which P dot is given by this one, and of course Q dot squared would be given by Q squared beta dot squared. Okay, so our kinetic energy now would then be equal to M times, this is um, P squared alpha dot squared plus 2pq alpha dot beta dot plus um, q squared beta dot squared, and this is for that part there, plus well, this is just now r dot. Notice that r dot squared is again the same. R dot, okay, is just equal to r times theta dot. So this is r squared theta dot squared. Okay, so this is now our kinetic energy. Okay, now we can actually solve the kinetic energy using a simpler approach, in which there's a theorem that says that the kinetic energy, the total the kinetic energy of the system is the kinetic energy of the center of mass plus the kinetic energy at the center of mass. Okay, let me repeat that. The kinetic energy of the center of mass, though, means, so meaning that is the kinetic energy, assuming that all of the masses that revolves around the center of mass is concentrated at that point, plus the kinetic energy at the center of mass, meaning that we fix this the center of mass, which in this case this is our center of mass, and calculate the relative kinetic energies of this. Okay, so we can actually do that, and you will arrive at this exact the same solution, and it's much easier because the center of mass is just this. Okay, as you can see, the kinetic energy of the center of mass, so let's call this T, uh, T naught, which is just equal to 1 half times what is the mass at the center of mass, that would be 2m. So you will have now times 2m times the vector of the pointing to the center of mass, that would just be equal to, and this is just equal to this one here, so that is p dot plus q dot squared. That's T naught. And the kinetic energy at the center of mass is just equal to the kinetic energy of this both. So that would be 1 half m times the kinetic energy of that one is that would be r squared theta dot squared plus 1 half m, this one here, r squared theta dot squared. And as you can see, this is exactly the same. Uh, this equation is exactly the same. Now, what is left before we can have our Lagrangian is the potential energy. So it's much easier to calculate the potential energy here. V1 is just equal to, let's calculate V1. That would just be this height here, which is P sine theta, plus that height there, this height there, that is Q sine beta, and then you have to subtract this one, minus R sine theta. So this means that this is M negative mg times P sine of alpha, sine of alpha, plus Q sine of beta minus R sine of theta. And our V2 would be equal to minus mg, and this is P sine of alpha plus Q sine of beta. This is now plus. Okay, you have to add this one here, R sine of theta. So that we will now have our Lagrangian. We will have now m times p squared alpha dot squared plus 2pq alpha dot beta dot, okay, plus q squared beta dot squared plus r squared theta dot squared minus v. So minus, okay, minus v1 minus v2. So this is just, how do we simplify this? Okay, you have mg, you have, okay, the r sine theta would cancel. As you can see here, you have plus here and then a minus. So v1 plus v2, okay, v1 plus v2 is, this will be cancelled out. So now v1 plus v2 is just, will be just this one here. So this is minus minus v, okay, minus minus the total energy, the total potential kinetic energy. So that would be plus mg uh, p sine alpha plus q sine of beta. Okay, this is now our kinetic energy. Let me put a red on this one. I mean, sorry, this is our final Lagrangian. Now, it will now be easy to calculate for the equations of motion. And as you can see uh, here, let's calculate now the equations of motion. Okay, let's calculate partial L over partial alpha. That would give us um, mg, mgp cosine alpha. So this is just mgp cosine of alpha. And partial L over partial alpha, uh, alpha dot would be equal to this one here. We have 2m, okay, we have 2, yeah, 2m plus, okay, we will have 2 times m p squared alpha dot plus 2pq beta dot plus 2pq beta dot. Okay, and of course, uh, taking the derivative of this is d over dt of partial L over partial alpha dot. That would give us um, okay, 2m p squared alpha double dot plus 2pq. Okay, did I miss something? No. 2pq beta double dot. Okay, And of course, if you take partial L over partial beta, okay, it will be the same. This is mg q uh, cosine of beta, and partial L over partial beta dot, that would give us, similarly, that would give us um, 2 times m q squared beta dot plus 2pq alpha dot. Okay, and we have here um, d over dt of partial L over partial alpha dot beta dot, that would give us 2 times m q squared beta double dot plus 2pq alpha double dot. And finally, for partial our r partial for our theta, partial theta, that would be equal to, this is 0, and um, partial L over partial theta dot would give us um, 2mr squared, 2mr squared theta dot. So d over dt of partial L over partial theta dot would give us 2mr squared theta double dot. Now, our three equations of motion, this is a coupled nonlinear equation. Is this nonlinear? Uh, yeah, it's nonlinear equation because there's a cosine, and yeah, there are cosines here. So the first equation in alpha, okay, that would give us this minus that. So how should I write this? I'll just write it in three terms. So you have, I think m would cancel out. So you have now p g cosine of alpha, okay, minus 2 p squared alpha double dot plus 2pq beta double dot equals 0. This is our equation 1, our first differential equation. Okay, this is d squared alpha over dt squared. And for beta, we would now have, we have qg cosine of beta minus um, 2q squared beta double dot. Okay, I think this should be a minus here. This is minus. So minus, um, this now becomes 4. So minus 4 pq, sorry, alpha, okay, 4 minus 4 pq alpha double dot equals 0. And the third equation in theta is just simple. We have d over dt of 2mr squared theta dot equals 0. Now here we have a conserved quantity. We see here that theta is actually a conserved quantity. Okay? Because it's not a function of theta. So there's the angular momentum is conserved locally. Where is it conserved? Here. But the total angular momentum of the system is not. Um, but the angular momentum at the center of mass, that is actually uh, given by theta dot, okay, r theta dot, it is conserved. So theta is actually a conserved quantity. Okay, so yeah, this is what we get, or this is actually, or we can actually express this as um, r squared theta double dot equals 0. We can use this equation. From here, we can solve theta independently. of alpha and beta. Okay, so how to solve alpha and beta? It's quite difficult to. Is it possible to solve this? We can actually express beta dot. We can substitute beta dot with this one here. Just equate. This is equal to beta dot, and substitute it to beta dot here. So our first equation would be all in alpha double dot, substituting beta double dot here, but still beta would would be would be present in the first equation even though you do substitution. This is actually a coupled nonlinear equation, and maybe the solution is purely numerical. Maybe there's no closed form solution here. You can try if you want to solve it. Okay, let me write this equation explicitly. um, that would just be I'll just use the positive for this one. So we would have 2p squared d squared alpha over dt squared plus 4pq d squared beta over dt squared minus pg cosine of alpha equals 0. This is your equation 1. And this equation would be um, 2q squared d squared beta over dt squared plus 4pq d squared alpha over dt squared minus qg cosine of beta equals 0. This is my equation 2. And of course, my equation 3 would be this. You have d squared theta over dt squared equals 0. You can take the r squared there. Let's use green for this and blue for this one and red for this one. Okay, so these are coupled equations. Okay, thank you for watching. Subscribe for more videos. We have more problems to solve here in this channel.